Here's a problem using compound interest. So let's look at the nice little formula here first and just maybe identify the variables here. So what compound interest is, we are taking simple interest and just adding interest on the interest, right? Simple interest isn't exactly practical. We don't really see it all that much in real life, like with bank loans or mortgages or whatever. Simple interest kind of just isn't a thing, but we can repeat simple interest, right? Taking interest on the interest, adding the interest to the principal, and interest on the interest on the interest on the interest, and so on. Anyway, that's kind of the basic idea of compound interest. We're just applying interest more than once per period, right? So anyway, we've got our nice formula here. We got a bunch of letters here. A. This is the amount that is in our account after T years. P is the principal. This is the amount that you start with. So this is our seed money or our investment, initial investment. R, this is the annual interest rate. So this is the interest rate per year. That's kind of important here. I don't think it comes up where you'll have interest rates expressed in a different way, but it is a big deal to be complete and correct that we are saying that it's an annual interest rate. Okay, so it's an annual interest rate. N is the number of compoundings per year, when T is the time in years. So there's your nice little formula. We know what all these letters mean. So let's take a look at a problem. So we're going to suppose that $1,000 is invested in an account earning 6% compounded quarterly. How much is in the account after 5 years? All right, well, let's do that. So for the first part, it would probably be in our best interest to maybe line up what all these values are, right? So for the first one, we don't know what A is. That's what we're after. P is our principal, so that's the amount we start with. So that is right here. So $1,000 is invested. So we got 1,000 bucks. All right. We have R, our rate per year. That's 6%. And we will want to write this as 0.06, right, without that percentage sign on there. Okay, we got R. N is the number of compoundings per year. So our investment here is compounded quarterly. So quarterly means 4 times a year. You're going to see maybe monthly. There's 12 months in a year. Quarterly, of course, there's 4 quarters in a year. Bi-monthly is something else. Biannually. But anyway, quarterly is going to be 4 times a year. So N is 4. Okay, T is time in years. So T for number 1, well, how much is in the account after 5 years? Well, T equal 5. Okay, so once we've done this little organization piece, all that's really left here is honestly calculator work, because we're just going to take and put all these in our nice formula here, right? So A of T, that's what we want. So we want A of 5. This is our principal times 1 plus, and then we're going to put our rate up here. We're just, plopping these values where they go in the nice formula, right? We got our rate, it's 0.06. And our number of compoundings is 4. And then we raise that to the N times T power. So we can do that, and this is a dollar amount. Now, looking back, I did not put this through a calculator, so I'm going to do that really quick and find out what that value is. Because, it's not like we're going to do this in your head, or maybe you will. I'm not quite that savvy to do that, but some people can do that. All right, so I cranked that through the calculator, and I got we're going to round this to 2 decimal point places because we're dealing with money. So 1, 3, 4, 6.86. rounded to the nearest cent. Okay, so that's how much our investment is worth after 5 years. That is wonderful. And now we can attack the second part of this problem. So how long will it take our investment to triple? Well, this one's a little more difficult. Let's start this one out by maybe writing, because we're looking for a time now, right? If we're going to do the same thing we did here, we could, right? Our amount, how much would it be if our investment tripled? Well, we want to triple that, so that'd be 3,000, right? Okay, and then our principal is the same, 1,000. Okay, our rate is the same, 0.06. Our n is the same, so that's 4. And then our t, that's what we want to know. So we can just, do pretty much the same process here. So we take all of these and we can plop these into our nice formula, right? So a of t, this is going to be 3,000. And plopping in the nice formula, there's a, and then we've got our principal times 1 plus our rate over our number of compoundings raised to the n times t power. Okay, now this one is a little bit more than calculator work, right? We're going to have to do a little bit of solving here. So let's do that. So we're just going to take this and solve for t. Well, I know that in the very near future, I'm just going to crank this through the calculator. So I'm just going to leave this, right? Because I know that I'm just going to put that through my calculator anyway. So, I mean, you could simplify this if you really wanted to, but, why do the work if we don't necessarily need to? We're going to end up cranking it through the calculator anyway at the end. So, I mean, if you're comfortable with simplifying it, you should do that. Anyway, we want to solve for t, so we want to get t alone. Our first step here is going to be to divide everything by 1,000, right? If we divide everything by 1,000, divide by 1,000 on both sides, this just goes away, and this becomes 3. Okay. So at this point, we can do things in a couple of different ways. I think that it's probably the easiest to use some of these properties of logarithms that let us get our variable out of the exponent position. So if we apply natural log to both sides, now because the natural log function is 1-to-1, this is a legal move. Maybe we can reference another video about 1-to-oneness to explain this. But this is a legal move, right? We can apply a natural log of both sides. If two things are equal, then so are the natural logs of those things. It's sort of like adding a number to both sides, but it's not exactly the same. Anyway, now we can apply properties of logarithms to get this 4t out of the exponent position, right? Because we know that if we have an exponent in this position in a logarithm, we can rewrite this as a factor instead of an exponent. We'll tack it out front. So this side's not changing. Left-hand side doesn't change. We still have natural log of 3. And then we know that this guy in the exponent position, we can write that as a factor. Natural log of this stuff. Okay. So now we are after t, and we are just dangerously close to finding what t is. We're going to come up here. So really, we just have to divide both sides by 4, and we have to divide both sides by this natural logarithm. So we're going to have natural log 3 over 4 times natural log 1 plus 0.06 over 4. And this is t. All right, now if we are strictly just asked for an exact value, this is the exact value. Now, if it wants us to round this value, that's when we're going to have to plug it into our calculator. And again, for some reason, it slipped my mind to put this in the calculator before I started, so I can do that real fast. So we got natural log of 3. Divide by 4 natural log. Alrighty. So when I cranked that through the calculator, I got 18.447 years. Now I don't know if, without going and looking what it's going to ask you for here, I would assume that it's going to ask you for it in years, and it'll probably tell you what decimal place to round it to. But do be careful with this, because this might not want it in years, strictly years. It could want it in years and months. So we would have to go 18 years and however many months 0.447 years is. But anyway, that's how we solve that nice couple of problems there. So really, I think the